Hello, welcome, and a very good evening indeed to our second part of the Rotozoomer Let's Code MS-DOS. Well, the Rotozoomer is a nice effect that we saw last episode, and it looks like this. You take a source image and map it to the screen while rotating and scaling it. And last week we went a bit through the maths behind that, how to program it sort of efficiently, but still we need to tune up the DOSBox cycles up to like 50,000-ish or something, which is I think a Pentium level or something. So it's still quite slow because it heavily relies on floating point arithmetic, which is slow on everything 486 or below, even slower on machines without an FPU, of course. So it's expensive. However, we already optimized the formulas quite heavily, so we try to pull out all of the arithmetic to the outside of the for loop so it doesn't get evaluated all the time, but there are some things like this which get evaluated for every scan line at least, and we need to do a few additions every pixel even. And while this is sort of fast, we can do better. And most certainly the floating point arithmetics are what's making this very slow on older machines like 386s or 486s. Even the 486 has still a pretty weak FPU, so we want to get rid of that part. And that means we need to do integer arithmetics. Floating point is called floating point because the numbers have a decimal point, something like 1.0, and then times 10 to the power of something, let's say -6. That would be equivalent to 0.000001. And basically you let the point float to wherever is necessary to represent the number so that it has a mantissa of something between 0 and 1 and then an exponent, which leads to pretty good accuracy. It's very useful, but it also requires a lot of computations on the FPU side. The integer operations on those older CPUs like the 486 or 386 are much faster than the floating point, even when there's a coprocessor installed. The 486 comes with a coprocessor, the 386 and 286 and even the 8086 can have one installed, but every floating point operation is expensive. So an integer operation will be cheaper. So what we could do is we could say, well, we have 16 bits, let's say we are coding 16-bit DOS mode here, which runs on 286s and even 8086s. So we have let's do it like this, 1, 2, 3, 4, 5, 6, 7, 8 bits here, and 1, 2, 3, 4, 5, 6, 7, 8 bits there. And we could just say, okay, let's say this here is the point, and it's not a floating point, it's a fixed point. It's always like this. We have 8 bits here for the decimal part and 8 bits here for the integer part. Maybe we have 7 bits and we have a sign bit in front, which gives us a range of roughly -127 point something, probably not 0, but something like 0.9, I don't know what, to plus 127 point something, with 8-bit accuracy here behind the decimal point. And this will be faster because this will use only the integer arithmetics of the CPU, and that will be very, very much faster, much less cycles on the CPU than the floating point operations. Even more so if your machine doesn't even have a floating point unit installed. For example, if you have an old 386, they would have an extra chip installed and most didn't. that's just a fact. The 486 was always with an FPU if it wasn't the SX variant, but the DX variant of the 486 always had an FPU. But still, even there, it would be faster to do it like this. The problem is, of course, we can only use numbers between -127 and 127, whereas with the floating point we have a huge range. We can display millions or even billions with relatively good accuracy. But also one floating point number will take up 80 bits instead of 16 bits, so it's much larger. We can store it as 32 or 64 bits in memory, but still running this on a real mode 386 or 286 requires quite a couple of cycles, because it will have to use at least 4 cycles to shift the bits around if you use a 64-bit double precision variable. But enough of that talk. So we want to do the fixed point. What are the rules here? Well, basically you can just add them and multiply them as normal integers. However, when you multiply them, you will have overflows basically left and right. So you will have to be careful. Plus you have to renormalize them by shifting right by the amount of bits that you're using on the right side. For example, if you used 8 bits as the decimal part, or we are probably going to use 7 bits to make space for the sign bit, etc., and for overflow reasons. So we probably will normalize the number after multiplications by shifting right by 7 bits, which will push the decimal point from way over here back to its normal position, basically. That sounds probably a bit abstract, but once you'll see the formulas, it will hopefully make sense. One other thing. Here in the floating point system, we just used the mass function, cosine and sine, etc. We need again the sine tables for the fixed point, and I use 3 different sine tables, one with 256 entries, one special one for the zooming part, for zooming in and out, which has an offset added to it. I won't talk about this right now. You can look it up later in the code, and I will link to the full code of both examples, floating point and fixed point, in the video description. Everything is on GitHub, so you can check it out and play with it, and you will probably figure out why I did that. And we will also take one sine function with 512 as its range for the translation of the whole image to get more accuracy. So we have 3 lookup tables instead of computing the sine functions on the fly. Also, you already see here that I'm going to use 7 bits of precision. That's why I take 2 to the power of 7, which is 128 actually, minus 127 as the scaling factor. And here for the, I'm not sure what I'm using that for. Let me look that up. I'm actually not sure where I'm using that. Oh, that's for the translation, yes. That's for the translation, so I'm using 63 values here. Why ever I chose 512 here, I don't know. You can play around with the sine tables and see what accuracy and what makes sense here. If you're not sure what the sine tables actually are, I will link now a card to the video where I talk about sine tables. Basically, it's to speed up computations and to have integer values instead of float values, and just look them up in memory instead of having to compute them, which is very expensive. So similar code will now be written for the fixed point. So we have here the if-def use float, and I'm gonna actually undefine this or rename this to no float. And now this else part will be active. And the interesting thing here is we can basically write the same code as we have with the floats here. We will have a lookup variable for the cosine, the current cosine, the current sine, the current zoom factor, and the current translation vector. but it won't be using this stuff, but rather using the lookup tables. We will also have the pre-computed j times sine and j times cosine, as well as the I times cosine, j times sine, and the other way around, which is basically our rotation matrix. But those will all be integer values instead. So let's go here and write just that code. So those will be constant because they won't change during the loop. We will use 16-bit signed integers because we can have positive and negative values, which is I think fine. We'll look the cosine up in the sine 256 table by using the time as an index, and the cosine is 1/4 pi, 1/4 pi, 1/2 pi, yeah, 1/2 pi ahead. So we add 1/4 of 256, which is 64, which gives us the correct phase shift to get the cosine of the sine table. And that's that. And of course the same goes for the sine, but here we can just take the value at t itself, modulo 256. The modulo is again because we have to wrap around. The sine function is periodic and we just store one full cycle, and every 256 elements, at least for this table, it will repeat. Furthermore, we will have to compute the translation vectors, and for that we take the other sine function, the sin zoom or sine zoom, and here we take just the value at t modulo 256, and oh sorry, not the translation, that's actually the zoom factor, which makes much more sense. Now we get to the translation parts. So tx equals sine 512 of t modulo, and now we have 512 values. And a thing for the y direction, we will take the cosine, because then we will create like a circular movement in the translation of the image. Sine versus cosine always gives a circle-ish feature, so 1/4 of 512 is 128. This gives us a cosine. And then we need to create, of course, the variables which will change, js and jc, which are the products of the runtime variable j and sine and cosine, and also the variables for the rotation matrix, which are ICJS and ISJC. That should be correct, yes. Now we can initialize those variables. So JS and JC are the outermost variables, and they are basically just the same as up here. So let's just copy that and maybe correct it where necessary. Let's delete that, copy that over there, and actually no, we can leave that. It's y plus ty times s and y plus ty times c. It's the exact same code because the math didn't change at this point. So next up we run the for loop. We again initialize j with 0, we initialize the pixel with the frame buffer pointer plus wherever the current pixel is. This is y times the width of the image plus the x coordinate. Furthermore, we will stop when j reaches our desired image height, and every loop we will increment j until we are finished, and we will move the pixel pointer a little bit further. Namely screen width minus width of the image, which I explained already last time, so that should be exactly the same as in the floating point case, so there's nothing new. If you have questions about that, check out the last video and it will hopefully become clear. Alright, Now it's time, the inner loop. Let's have a peek. We initialized ICJS and ISJC. And what do you know? It should look more or less the same. It should be x plus tx times c minus js and times s plus jc. This is basically the rotation matrix evaluated at this point. We just need to incrementally update it. Nothing has changed yet. So now comes the inner loop. Now we loop over every pixel. I equals 0 and I is less than the width of the desired image, and we increment I, which is just fine. Now comes the more complicated part. Last time we had this lookup, which already looks a bit weird. We had to multiply the rotation matrix by the zoom factor, cast that to an integer, and do the modular operation so we don't run out of the image but stay inside the image. So we get this tiling effect that we see a lot of small images. And this is more or less the same, looks slightly different. So u equals, well, we take the ICJS value and now we need to renormalize it at first because we did a multiplication up here. So we shifted right by 7. Better to put parentheses around it because this operator is a very low priority. So we will get the wrong answer if we don't do that. And then we multiply it by the zoom factor just as we did above. But again, we did a multiplication, so that means we again need to renormalize. So we put another shift operator around that. And this will give us the normalized number again. And now the last one is basically the same as above, but for speed reasons I actually, and I know the size of my image, I actually figured out that we can also use just an AND operator with 0x7f, which you would have to adjust with the correct image size, but here, yeah, if you know that you have such a small image, you can use that to speed it up. And that should be that actually. The V operation will be similar, except of course we use ISJC, and that should do it, yeah. The next part should be exactly the same, so we can copy all the pixel setting, and we can even copy the update of the rotation matrix if I were to press the right buttons. Everything is here the same because they are just additions and they work in floating point the same as in fixed point. So here we go. Something is indented differently. Why did I change something? Oh yes, I should probably have put that here, and there should be a closing brace over there. So that should be right, yes. So in the inner loop we get the color from the image, set the pixel, and if mode Y is enabled we double the pixel, so that's why this is there. And then we update the rotation matrix by adding the cosine and the sine. It's really exactly the same as in the floating point, so it's really not that hard to understand, and that it should work the same. And same goes for the outer loop. We update our JS and JC values, which are the products of J with the sine and the cosine. We can just put that there and that should work. And that's actually all there is. This is very little code actually to make it run hopefully faster. Let's try to run it. Remember that it looked already pretty smooth with 50,000 cycles. I haven't tested it, so let's see if it works. And it does, and I think it looks smoother. You see, in the rotation you can see a little bit of quantization because we use only 7 bits. It looks a bit jerky while rotating, but at the same time it looks, in my opinion, really fluid. Even more so than with the floating point values. We can even turn down the cycles now and make it run this is roughly 486 speed-ish, around 20 to 30 megahertz. It's still slow. The best way to accelerate this now would be to rewrite this in assembly language and to actually use 32-bit operations. 32-bit operations will make this incredibly faster and also more accurate, because you can use much higher accuracy floating point, fixed point arithmetics, so that you don't get this stutter. Alternatively, you could leave it in 16-bit and rewrite an assembly language to get it maybe to run on a 286, but maybe we would need to switch to mode Y with the pixel doubling then. But still, I think this already looks pretty neat. So this is the speed that we will get when we run it on my 486 33 MHz, maybe a bit faster. But I think for coding in Turbo C 2.0 in 16 bits in real mode, this is actually a pretty good result without resorting to any assembly language. And yeah, maybe as a homework you guys can rewrite this using assembly language and 32-bit operations, and then we can have a benchmark and see that how much faster we can get this actually. And of course, my 486 has an ISA card. It's probably fast enough, it's a pretty decent card, but having a local bus card like a Visa local bus or PCI local bus will even make it faster. Anyway, this should show you that a lot of the demo effects that rely on floating point can actually be rewritten in fixed point arithmetics, but you have to be careful about the sizes of the numbers and the normalization. So having fast FPUs on modern machines is actually a godsend. It makes a lot of coding so much easier to work with. And back in the day I didn't understand that because my math skills weren't good enough, etc. But by now I can actually appreciate what the demo coders did when they coded stuff like this. And I bet that Second Reality also uses fixed integer arithmetics. I haven't checked the code. Again, you can find it on GitHub, both my code and especially the probably much better Future Crew code for this effect. But I think from both stuff sources you can learn a lot. And for now, that's it, I think. Make sure that you hit the subscribe button if you haven't. Click the like button, of course, and definitely leave a comment what you thought about this. Did you ever use fixed points or floating points? Do you know what that stuff is? Do you need more explanations? I can delve into more depth, of course. And you can also support me otherwise on Patreon, Ko-Fi or PayPal if you want to. If you have troubles at the moment, no big deal. It's enough that you watch this stuff. If you maybe watch the ads before, that helps me also a bit. And I hope to see you in the next Let's Code episode, or maybe even the next video, because that will probably be something very different. But until then, I wish you a very good evening and say goodbye.